Today I want to just do a quick review of power series. This is done in the book in section 5.1, so be sure to read everything they say about power series very carefully. And of course, if you have your old calculus textbook, you can review power series there too. Here's the basic idea. We start with the power series. This is a power series, we say, centered at A. So here, this number A will be called the center of the power series. And when we express a power series, when we express a function as a power series, what we mean is that for each x, you plug that in here, you compute the value of the series, and that gives you the output f of x. Of course, having a series representation means that the first and most important question you'll ask is, does this series even converge? And when we talk about the domain of this function f, defined by the power series in this manner, we mean exactly the set of x's for which this power series converges. Now, luckily, we know this power series converges on some interval centered at A with some radius that we'll call capital R. This is called the radius of convergence. At least in general, there'll be a radius of convergence, and the power series will converge on an interval of that radius centered at A. In the worst case, this radius of convergence might be 0, in which case, instead of having an actual interval of convergence, you'd have a degenerate interval, just a single point, A, on which the series converges. And certainly the series will always converge at A because all the terms will be 0, except for the 0 term. So let me write out what the terms will look like. By convention, then, we have the first term is C0, and x minus a to the 0th power is just 1. The n equals 1 term is C1, x minus a. The n equals 2 term is C2, x minus a squared, etc. Now, it's not difficult to find this radius of convergence in most situations. The ratio test can be applied, and as a simple result of the ratio test, we get the following method of computing the radius of convergence R. First, compute this number, which is the limit as n goes to infinity of the absolute value of Cn plus 1 over Cn. You just look at the ratios of successive coefficients, C sub n. Now, as long as this is a finite number, so if this limit exists and it's between 0 and infinity, it's some finite number. It can't be negative because, of course, we've taken absolute values here, so it's positive. Then we know that the radius of convergence R is just 1 over that number. And so then by convention, we say R equals infinity if this limit is 0, and R equals 0 if this limit is infinity. And when R equals 0, that means that this series will only converge at the one point x equals a. When R equals infinity, it means the series converges on the whole real line, minus infinity to infinity. But in general, in the most typical case here, if R is some finite number, then the series converges, and in fact converges absolutely. I should put that in here. On this interval from a minus r to a plus r. This is an interval centered at a of radius r. It diverges on the set minus infinity to a minus r union a plus r to infinity. And the only points we've left out are these endpoints, a minus r and a plus r. These are the endpoints of this interval of convergence. And sometimes, depending on the coefficient C sub n, sometimes you get convergence at one endpoint or the other endpoint, or both, or neither. All the possibilities are there. For everything we're going to do, we're going to be looking eventually for solutions to differential equations using power series representations, and typically we'll be interested in finding a solution that's valid on an open interval. So most of the time we're not going to worry about what happens at the endpoints of this interval, but you should know if you care about what happens at the endpoints of the interval, just test those separately using whatever test for series convergence you can find. Here are some of the most important facts, certainly for us as we're working with power series. When you have a function represented by a power series, f of x is the sum of c sub n times x minus a to the n, and again I'll write that here as f of x equals c naught plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed plus etc. When you have a function represented by a power series, the key is we can apply calculus to it. We can differentiate and integrate the function by differentiating and integrating the power series term by term. And that makes power series behave, from this calculus standpoint, as big old polynomials. We can think of them as infinite degree polynomials, but don't say that because, of course, they're not polynomials, they're infinite series, and you have to deal with convergence issues. But when it comes to differentiation and integration, they behave like term by term, like polynomials do. You can differentiate and integrate term by term. So here's the basic way we can go about that. If you have a function given by this power series representation, when you differentiate it, you can differentiate term by term. And if we just take the formula here for the nth term, n equals 0, 1, 2, 3, etc., we differentiate that again with here with respect to x. The derivative is just n times c sub n times x minus a to the n minus 1. So we get this. And we're summing that from n equals 0 to infinity. Now, one thing you can notice is that the n equals 0 term gives you 0 here. So we can drop that and write that as the sum from n equals 1 to infinity of n c sub n x minus a to the n. Let me show you what that looks like written out term by term. And of course, if you want to write it out term by term, you could start with this representation up here and just differentiate term by term. The c naught disappears when you differentiate it. The derivative of c1 times x minus a is just c1. The derivative of c2 times x minus a squared is, by the chain rule here, 2c2 times x minus a. The derivative of the next term gives you 3c3 x minus a squared. And it keeps going like that. And you'll see that's what we get when we start this at n equals 1. Nothing wrong with leaving it as n equals 0, of course. Started with n equals 1 going to infinity of n c sub n, that's 1 c sub 1, x minus a to the n minus 1. So here we have 1 times x minus a to the 0th, 2 times c2 times x minus a to the first power, etc. So we can differentiate f. And the final thing, which I haven't mentioned so far, but I have it written down here, that if you start with the power series with radius of convergence capital R, so that it converges absolutely on this open interval, then the derivative will have the same radius of convergence, and the derivative will converge absolutely on this same open interval. What happens on the endpoints is actually a much trickier issue. As I said, we're not going to be quite so interested in what happens at the endpoints, but there are some weird examples where you can have a power series with radius of convergence 1, for example. The derivative will, of course, give you, as I've just claimed, and one can prove this, a power series with the same radius of convergence 1. But even if the first one might have converged at the endpoints, the derivative might no longer converge at either endpoint, or maybe one no longer converges at one of them. Convergence behavior at the endpoints can change, but the radius of convergence must stay the same. And since we're interested primarily in looking at functions on open interval domains, that's really the important thing for us, and that's all we care about. Now, here's what I want you to look at. Here's an expression for f prime of x. Here it is written out term by term, and you should always be comfortable doing that. Here we started with this series. We ignored the n equals 0 term because that was 0. We wrote it like this. Now I'm going to shift the index, and this is going to be an important thing for us to use later as we start comparing different power series. The standard form of a power series has constants times this quantity x minus a, where a is the center of the series, this quantity to the nth power. that's just a standard form, so we can use that as a reference, and yet now the way we've written it is to have x minus a to the n minus first power. So we'd like to replace n minus 1 by n. In other words, shift the index n, change n equals 1 to 0, and move this to just n instead of n minus 1. So we can do that. So wherever you see an n minus 1 here, put an n. When you see an n, put an n plus 1. But that means I'm no longer starting when n equals 1. I'm starting when the new n is 0. So that becomes the sum from n equals 0 to infinity of n plus 1, c sub n plus 1, x minus a to the n. And check that this gives you the exact same series as this. In this case, when n equals 0, we get 1 times c sub 1 times x minus a to the 0th power. That's exactly this term, c sub 1. When n equals 1, we get this term, 2c sub 2, x minus a. When n equals 2, we get this term, etc. We get the exact same terms. Make sure you convince yourself we get the same terms here and here. So this shows you how you can legitimately shift the index on your power series without changing what that series is. Now, if you can take a power series that represents a function and differentiate it to get a series that represents the derivative of the function, you can do it again. So if f prime of x is given by this series, f double prime is just the derivative of this series. So we can take, I believe I use this form here, differentiate each term. The derivative of n c sub n x minus a to the n minus 1 is just n times n minus 1 c sub n x minus a to the n minus 2. And again, we're starting from n equals 0. But now notice, when we write out the terms here, if I differentiate again, I'm just going to use these and do term by term differentiation. That goes to 0. This becomes 2c sub 2. The next term is 3 times 2, so we get 6 c sub 3 x minus a. The next term here would have been 4 c sub 4 x minus a cubed. So the next term here would be 12 c sub 4 x minus a squared, and it continues like that. We can shift the index because these first two terms, when n equals 0 and when n equals 1, both give you 0. So I can just shift to start when n equals 2. I haven't shifted the index yet. I've just dropped the first two terms, I should say, from this n and go from 2 to infinity. And then I can actually shift my index. I'll say that should be a 0 here now. And write that as the sum from n equals 0 to infinity of, instead of n, I'll put n plus 2. So instead of n minus 1, I put n plus 1, and I'm replacing the n minus 2 by an n. Oh, boy, I've done a lot of bad things here. This should be c sub n plus 2 here. So check, since I typed it all incorrectly, check that the way I've written it here actually works with this series. If I sum from n equals 0 to infinity, n plus 2 times n plus 1 times c sub n plus 2 times x minus a to the n. When n equals 0, you get exactly 2c sub 2 times x minus a to the 0th, which is 1. When n equals 1, you get 3 times 2, which is 6 c sub 3 x minus a to the first power. When n equals 2, you get this term, etc. So here's a way to write a power series for f double prime that's in standard form. In other words, some constants times x minus a to the nth power, starting when n equals 0. Here's the expression for f prime. Now, this power series for f double prime will again be valid, by which I mean absolutely convergent on this and equal to f double prime on this exact same interval, at least on the open interval, a minus r to a plus r. And of course, we could do it once, we could do it twice, so we could just keep going. You could easily write down for yourself an expression for f triple prime, f4, f5, etc., all the higher derivatives of f, which tells you something amazing, that the functions represented by power series in this way are infinitely differentiable. If you have a function that's represented by a power series with a positive radius of convergence, so it represents an honest-to-goodness function on this interval of radius r, it's infinitely differentiable, and all of its derivatives will be valid on this exact same open interval. What happens at the endpoints, again, can change from one derivative to other derivatives, but on this open interval, everything is beautiful and you have an infinitely differentiable function. We call functions that are represented by power series like this analytic. So if f has a power series representation, say centered at A, f of x is the sum of c sub n, x minus a to the n equals 0 to infinity, with a radius of convergence r, which is positive. We certainly won't call a function analytic if the radius of convergence is 0. Then it's only defined at one point, then it's a nasty, useless function. But if it has a positive radius of convergence and a power series representation, we say f is analytic. Sometimes people will use the term real analytic because we're talking about everything here with real numbers. F is analytic at A. And often it's important to make the distinction between real analytic and complex analytic, because the notion of an analytic function is going to be important for us as we're using power series representations. But when you study, and I mentioned in class that I strongly recommend that you take Math 408 and 409 if you're at all interested in learning a lot more about functions of a complex variable. Being analytic is fundamentally important for functions of a complex variable. It's a direct extension of what we're saying here. Basically means you have a power series representation over complex numbers. But you'll see when you take those classes how that's more fundamentally important in everything that's done in the theory of complex variables. But we still use the same term analytic to denote functions which have such power series representations with a positive radius of convergence, even for real valued functions.